The evolution of battery technology for camera applications, trail cameras, SIM-based surveillance cameras, and beyond. Battery technology has long been an essential component in the development and success of portable devices, especially cameras. From trail cameras used by wildlife photographers and researchers to SIM-based surveillance cameras for security applications, the demand for reliable, long-lasting batteries has continuously grown over the years. These cameras must be powered by batteries capable of handling a range of challenges, such as extreme temperatures, extended intervals between recharges, and providing steady power output to capture critical moments. Understanding the history of battery technology for these camera applications involves looking at the numerous advancements, breakthroughs, and challenges that have shaped the industry. Moreover, the story of battery development is also one of field testing and innovation, driven by passionate individuals who continuously pushed for batteries that would endure harsh conditions while maintaining peak performance metrics like longevity, temperature tolerance, and reliability. This exploration takes us from the early days of camera battery development to the field tests conducted by adventurers and researchers, and culminates in breakthroughs in material science that have resulted in modern battery technologies. These technologies are now used in camera devices with far more efficiency than ever imagined. Early camera battery technology. The first portable cameras emerged in the late 19th and early 20th centuries, but they were cumbersome, required significant amounts of power, and lacked the necessary energy source for long-term field use. Early versions of these cameras were manually operated, and it wasn't until the 1930s that the first electric cameras emerged. However, these cameras used heavy, non-rechargeable dry cell batteries that had limited power capacity, which made them impractical for extensive use in the field. One of the earliest types of batteries used for camera applications was the zinc-carbon battery, developed in the 1860s. Zinc-carbon batteries were relatively inexpensive to produce and provided a stable source of energy for low-drain devices. Despite their utility, these batteries had significant shortcomings, particularly their low energy density and poor performance in cold temperatures. This posed a major problem for trail cameras and surveillance devices, which needed to operate reliably in harsh outdoor conditions. In the early days, explorers, wildlife photographers, and amateur researchers carried multiple zinc-carbon batteries into the field, knowing that the power output would be limited, forcing them to constantly change batteries. These early challenges signaled a need for more efficient power sources, laying the groundwork for future innovations. A major leap in battery technology came with the introduction of rechargeable nickel-cadmium (NiCad) batteries in the mid-20th century. Developed in 1899 by Waldemar Jungner, NiCad batteries offered an improvement over the earlier zinc-carbon models by providing higher energy density and the ability to be recharged multiple times. These batteries became a game-changer for early camera users, especially wildlife photographers and researchers who needed to use their devices for extended periods without the constant need to replace batteries. For trail cameras in particular, NiCad batteries provided a temporary solution to the power problem. However, these batteries also had their own set of challenges. NiCad batteries suffered from limited temperature tolerance and a memory effect, which caused the battery to lose capacity, if not fully discharged between charges. This memory effect significantly reduced their lifespan and reliability, especially for users in the field who couldn't always ensure proper battery cycling. The rise of specialized batteries. As the need for longer-lasting, more reliable batteries grew, the next major breakthrough arrived with the development of lithium-ion batteries in the late 20th century. Pioneered by John Goodenough, Akira Yoshino, and Stanley Whittingham, lithium-ion batteries revolutionized portable electronics. Lithium-ion batteries had far greater energy density than NiCad batteries, and crucially, they eliminated the memory effect, making them more efficient and reliable. For trail cameras and surveillance systems, lithium-ion batteries represented the ideal solution. They were lightweight, provided long-lasting power, and could be left in the field for extended periods without the need for frequent battery changes or maintenance. This was especially beneficial for wildlife researchers and security professionals who needed reliable, uninterrupted power for weeks or months at a time. Alkaline batteries were another widely used power source for camera devices in the 1990s and early 2000s. These batteries offered better energy density compared to zinc-carbon batteries and were readily available in most markets, making them a popular option for low-maintenance devices like trail cameras and early SIM-based surveillance systems. However, like their predecessors, alkaline batteries had significant limitations, including a limited lifespan in high-drain applications. Additionally, they were not rechargeable, which made their usage more expensive over time. Most notably, alkaline batteries perform poorly in cold environments, a critical drawback for outdoor cameras that needed to operate in a wide range of temperatures, from freezing winters to hot summers. As the use of trail cameras and surveillance systems expanded, it became increasingly clear that camera batteries needed to be more specialized. Manufacturers began to collaborate more closely with researchers, wildlife photographers, and security professionals to develop batteries that could withstand the real-world challenges of field use. The role of early field testers, particularly wildlife researchers and security professionals, cannot be understated. Individuals like Dr. George Schaller, a renowned conservationist known for his work tracking snow leopards in Central Asia, were instrumental in pushing the limits of existing battery technologies. These researchers would spend days or weeks in the field, often under harsh conditions, only to find that their batteries would fail due to poor temperature tolerance or short lifespans. The demand for a more reliable, longer-lasting power source became one of the driving forces behind the innovations in battery technology. Field testing, the role of innovators. One of the key aspects of advancing battery technology for camera applications was the role of field testers. The feedback provided by photographers, researchers, and security experts helped manufacturers understand the real-world demands placed on their products. Field testers often operated in extreme environments, facing everything from sub-zero temperatures to sweltering heat, and their experiences were invaluable in identifying the strengths and weaknesses of various battery designs. Wildlife researchers and photographers, in particular, contributed significantly to the evolution of camera batteries. Some of the pioneers of field testing, such as photographers working with National Geographic, pushed the boundaries of battery performance. Figures like Steve Winter and Nick Nichols, known for their breathtaking wildlife photography, would spend weeks or months in remote jungles, deserts, or mountains, relying heavily on trail cameras to capture rare and elusive wildlife behavior. The challenges they faced with inadequate battery life or malfunctioning power sources often meant the difference between success and failure in capturing important photographic and scientific data. Battery manufacturers worked closely with these field testers to design and refine battery technology that could meet the extreme demands of the field. Paul J. Rogue, a key engineer in battery technology development, worked tirelessly alongside camera manufacturers, constantly innovating and improving battery designs based on the feedback from trail camera users, security experts, and wildlife researchers. For many of these field testers, one of the biggest challenges was simply ensuring that their batteries lasted long enough to complete their missions. Changing batteries in the field was often impractical, and carrying multiple spare batteries was cumbersome and inefficient. Therefore, the push for batteries with greater longevity became a critical focus for manufacturers. Longevity and power output challenges. The introduction of modern digital cameras, with their increasing technological sophistication, significantly raised the stakes when it came to battery longevity and power output. Cameras began to require more power to operate high-resolution sensors, motion detectors, infrared LEDs for nighttime photography, and wireless connectivity for real-time image transmission. All of these features placed additional energy demands on batteries. And ensuring that these systems remained operational for long periods became a central concern for manufacturers and users alike. To address this challenge, battery developers focused on increasing energy density, the amount of energy that can be stored in a battery relative to its size. Lithium-ion batteries became the de facto standard for high-performance cameras due to their high energy density. But even they sometimes proved insufficient for the extended field use demanded by trail cameras and surveillance systems. Some camera manufacturers began incorporating external power options, such as solar panels or larger battery packs, to meet these extended power needs. Solar panels in particular became an important solution for trail cameras placed in remote locations. By using solar power to recharge the battery, these cameras could operate indefinitely as long as there was enough sunlight. However, solar panels weren't always practical in heavily wooded areas or regions with minimal sunlight, so the quest for longer-lasting, more efficient batteries continued. Advances in battery chemistry also contributed to addressing the challenges of longevity and power output. Lithium polymer, LiPo, batteries, for example, emerged as a lighter, more flexible alternative to lithium-ion batteries. While they provided similar energy densities, LiPo batteries could be designed in more compact form factors, making them ideal for smaller cameras without sacrificing performance. At the same time, manufacturers explored other battery chemistries, such as nickel metal hydride, NiMH, and lithium iron phosphate, LiPo4, for their potential to deliver longer-lasting, more consistent power. NiMH batteries were often used in lower power devices, like basic trail cameras, while LiPo4 batteries offered better temperature stability and longer lifespans, making them ideal for use in extreme environments. Despite these advances, designing a battery that could deliver consistent power for weeks or months in the field remained a challenge. Many field testers reported that even the most advanced batteries would often fail after extended periods in harsh environments, leading to ongoing research and development to overcome these obstacles. Temperature tolerance and durability. Temperature tolerance has always been a critical challenge for camera batteries. Batteries operate through chemical reactions, and extreme temperatures, whether too hot or too cold, can slow down or disrupt these reactions, leading to reduced performance and shorter lifespans. For camera users who worked in extreme environments, such as Arctic researchers or those studying wildlife in desert regions, temperature-related battery failure was a persistent problem. In cold weather, for example, battery performance suffers because the chemical reactions inside the battery slow down, resulting in reduced power output. Lithium-ion batteries, while better suited for cold temperatures than earlier technologies, still had limitations. As a result, some manufacturers began developing cold weather batteries with advanced insulation or built-in heating mechanisms to help maintain a consistent operating temperature. Wildlife photographers working in regions like Alaska or Siberia often had to develop creative solutions to keep their camera batteries functioning in freezing temperatures. Some field testers used insulated cases or external heating packs to maintain the battery's temperature, while others resorted to constantly swapping out batteries and warming the spares inside their clothing or sleeping bags. Similarly, durability was a key concern for camera batteries used in extreme environments. Batteries not only needed to withstand temperature fluctuations, but also had to survive exposure to moisture, dust, and physical impact. Trail cameras, which were often placed in rugged, remote locations, required waterproof and shockproof battery housings to prevent failures due to environmental exposure. Field testers played a crucial role in identifying the vulnerabilities of early battery designs. Through their feedback, manufacturers were able to develop more robust, durable battery solutions capable of withstanding the rigors of outdoor use. Camera batteries were increasingly designed with tough, weatherproof housings to protect the delicate internal components from the elements, ensuring that even in the most challenging environments, the battery would continue to deliver reliable power. Breakthroughs in battery materials. As the limitations of traditional lithium-ion and NiCad batteries became more apparent, researchers began exploring new materials and technologies to push the boundaries of battery performance. One of the most exciting developments in recent years has been the rise of solid-state battery technology. Unlike conventional batteries, which use a liquid or gel electrolyte, solid-state batteries use a solid electrolyte. This offers several significant advantages, including higher energy density, improved safety, since there's less risk of leaking or combustion, and better performance across a wider range of temperatures. Solid-state batteries could potentially solve many of the problems faced by users of trail cameras and surveillance systems by providing longer-lasting power and better durability in extreme environments. For camera applications, solid-state batteries hold enormous promise. Their higher energy density could allow manufacturers to produce smaller, lighter batteries capable of lasting for months without requiring recharges. Additionally, their superior temperature tolerance would make them ideal for cameras deployed in harsh environments where temperature fluctuations are common. While solid-state batteries are still in the development and early commercialization stages, many experts believe they could eventually replace lithium-ion batteries as the standard for portable electronics. Another important area of research has focused on sustainability and battery recycling. As the demand for portable electronics continues to grow, so too does the environmental impact of battery production and disposal. Researchers have made significant strides in developing more sustainable battery materials and recycling processes to reduce the environmental footprint of camera batteries. Some field testers, particularly environmental researchers and conservationists, have been at the forefront of the movement towards more sustainable battery options. Their demand for environmentally friendly products has helped push manufacturers to explore new, eco-friendly battery technologies such as lithium-sulfur and sodium-ion batteries, which offer promising alternatives to traditional lithium-ion chemistry. Future trends and innovations. In addition to breakthroughs in battery chemistry, several other exciting trends are emerging in the field of battery technology for camera applications. One of the most significant developments has been the growing use of solar power to extend battery life. Many trail cameras and surveillance systems now offer solar panels as an option to recharge the battery while the camera is in use. This allows the camera to operate indefinitely as long as there is sufficient sunlight, making it an attractive solution for cameras placed in remote areas. Solar-powered cameras are particularly useful for security applications and wildlife research, where it may be impractical to visit the camera site frequently to replace or recharge batteries. Field testers have been instrumental in refining solar-powered camera systems, providing valuable feedback on how solar panels perform in different environments. This has led to improvements in the efficiency of solar charging systems, making them more reliable, even in challenging conditions, such as shaded areas or regions with variable sunlight. Wireless charging is another emerging trend that could revolutionize camera battery technology. Wireless charging technology would allow users to recharge their camera batteries without needing to physically connect the camera to a power source. This could significantly reduce wear and tear on camera ports and improve the longevity of the devices. In addition to wireless charging, energy harvesting is another promising technology on the horizon. Energy harvesting systems would allow cameras to capture and convert energy from their environment, such as vibrations, temperature changes, or ambient light, into usable power, reducing the need for frequent battery changes or recharges. Although energy harvesting is still in its early stages of development, it holds great potential for improving the convenience and efficiency of camera power systems. The history of battery technology for camera applications is a story of relentless innovation and adaptation, driven by the needs of field testers, researchers, and professionals who have pushed the boundaries of what is possible. From the early days of zinc-carbon and NiCad batteries, to the breakthroughs in lithium-ion and solid-state technologies, the evolution of camera batteries has been a key factor in the success of portable cameras for wildlife research, security, and photography. The role of innovators in the field cannot be overstated. Through their real-world experiences and feedback, manufacturers have been able to design and refine batteries that meet the demanding requirements of extreme environments. These efforts have resulted in batteries that are more reliable, durable, and capable of powering cameras for extended periods. As new materials and technologies continue to emerge, the future of camera battery technology looks brighter than ever. With advancements in solid-state batteries, solar power, wireless charging, and energy harvesting, the next generation of camera batteries will be more powerful, versatile, and environmentally friendly than ever before. The history of battery technology for camera applications is one of continuous progress, and the innovations of tomorrow will further push the limits of what portable cameras can achieve.